Let's look now at linear inequalities in one variable. Let's begin with the definition. A linear inequality in one variable is an inequality, and here's what we're defining. Linear inequality in one variable is an inequality that can be written in one of the following forms. Ax plus b is greater than c. Ax plus b is less than c. Ax plus b is greater than or equal to c, or Ax plus b is less than or equal to c, where a, b, and c are constants, with the only restriction being that a should not be 0. Where a, b, c are constant real numbers, and specifically a should not be 0. Because if a is 0, then these disappear and you're simply left with an inequality without any variables. And here we're looking at an inequality in one variable. Whenever you have an inequality like this, these are called exclusive inequalities. Whereas these right here are referred to as inclusive inequalities. The difference being that here you exclude that value as part of your solutions, meaning this cannot equal to c. It has to be specifically greater than. You're excluding the possibility that it can equal to c. Whereas over here, it's almost exactly the same, except here it's being included. You're including the possibility that this is equal to c along with it being greater than. So you either exclude this value as being equal to this, or you include it as being equal to this. You include it in the set. To make that language a little clearer, let's go ahead and look at the most simple examples of linear inequalities in one variable, and that's the case where a is equal to 1. So here you don't have the coefficient there, it's just x, and where b is equal to 0. So here you're just left with x is either greater than or less than, greater than equal to, or less than or equal to a number. So here are the simplest examples of inequalities that would qualify as linear inequalities in one variable. Let's say you have x is greater than 2. Okay? You can think of this as the points on a number line that are to the right of the number 2. So here is our number line. Here's 0, 1, 2, 3, 4, and so forth. When we say we want x greater than 2, that means from this 2 to the right, we want to include all of these as part of our solutions. Now notice, this does not include the number 2. We want numbers that are to the right of 2, that are greater than 2. That does not include the number 2 itself. So that would only include everything on this side, and it would exclude the number 2. Hence the name, an exclusive inequality. The notation, whenever you have something like this and you're trying to graph it, there are a few different notations that can be used, but what we're going to use is, there's a reason why we want to use this one in particular, is whenever you exclude a number from part of a set, if that number is on the end of that set, we're going to use a round parenthesis. If the number is excluded, the round parenthesis points in the direction of the points that are not excluded. So here we want all of our points to the right, so here the parenthesis opens facing to the right. Now let's say we flip that around. Let's say we have the other exclusive inequality where we have x is less than 2. Well, now this is going to look very similar. We're going to have all of the points that are to one side of the number 2, but now instead of wanting all the points that are to the right of the number 2, now we want all the points that are to the left of the number 2. all of this stuff going this way. Once again, the number 2 is not included in this set. We're saying we want x to be less than 2, never equal. So here, this number 2 is excluded from being a solution of this inequality. So we're going to put a parenthesis here, and again, the parenthesis opens this direction, right? The cup is facing in this direction, like this. Now, one thing to note is that when we draw them this way, this does keep going forever. It's not like it stops right here or here. This does keep on going forever in the appropriate direction. Note that we have a symbol for that. When something goes on forever and ever and ever, we use this symbol here. This stands for infinity. Note, infinity is not a number. It's just a symbol that's used to signify that you're going to go forever. Really, it's signifying that there is no number. Rather, you just keep going without ever stopping. You can go forever in the negative direction, and so we usually put a negative in front of that. We say it's like saying negative infinity. Again, infinity is not a number. It's not like we took infinity and multiplied it times -1 and got negative infinity. Rather, this negative infinity signifies that you're going to go forever in the direction of the negative numbers. After all, negative numbers are to the left. -1, -2, -3, and so forth. Okay? Just like that. Now, if we have an inclusive inequality, things change very little. In fact, they don't change at all except at a single spot. Because if x is greater than or equal to 2, that's almost exactly the same as saying x is greater than 2. Because you still want everything to the right of the number 2. The only difference is now we want to include the number 2 as part of our solutions. Here, x is greater than 2. It can't be 2, it just has to be to the right of 2. But here, this is x is greater than or equal to 2. So it's greater than, okay, good, we're happy. If it's equal to 2, if it's that number right there, we're also happy. So we're going to include this number, and the symbol we're going to use to include a number visually is a square bracket. The square bracket signifies that that number is where your solutions start, and that number itself is also included as part of my solutions. Like this. And finally, if you're going to go back the other way, if you say x is less than or equal to 2, then it's going to be almost exactly the same as this one. We're going to want everything to the left of 2. But now when we get to the number 2, we also want to include that because we're okay if x is less than 2 or if it's equal to 2. So to signify the fact that that 2 is part of our answers now, we're going to use a square bracket as opposed to the round parenthesis that we had before. Okay? So inclusive inequalities that include the boundary, that include that number on the end, use a square bracket. Exclusive inequalities that do not include the number on the end, those use a round parenthesis. Just like that. Now, whenever we have an inequality, we can represent it by drawing it on the number line. But instead of having to draw the entire number line, we can often get a similar experience, we can often get a similar illustration without actually having to draw out the full number line. This is called interval notation. And what interval notation does is it mimics the illustration of the number line without actually having to draw out the line. So here's how this goes. If I have x is greater than 2, that means I want everything from 2 going forever to the right. Well, we have a symbol for going forever to the right. That's the infinity symbol. Okay, so we want everything from 2 to infinity. Okay, so let's write that. We're going to write from 2 to infinity. Okay? Note that it does maintain the same order. Here on this illustration, 2 is on the left, and infinity, the symbol for infinity is on the right because you're going forever to the right. So over here, from left to right, we're using the same symbols in the same order. Now, around the number 2, right here, we notice a parenthesis. So when we write this in interval notation, we're going to put a parenthesis right in front of the 2 to signify that we go on the left, we go as far as the number 2, but we don't include it. We exclude it. On an infinity, you always put a parenthesis no matter what. It doesn't matter if it's an inclusive or exclusive inequality. We always put in parentheses around either infinity or negative infinity symbols. The idea being that if you use a square bracket, it's because that number is part of your solutions. Infinity is not a number, so it can't be part of your solutions, ever, no matter what. Okay, so then we always use a round parenthesis around these. If we wanted to write this in interval notation, again, from left to right, first we see a minus infinity, and then on the right we see the number 2. We always have a parenthesis around infinities, no matter what. And then here, if we exclude the number 2, then that would use a round parenthesis. So this represents this illustration using interval notation. This next one is almost identical to the first one. The pictures are almost identical, so the interval notation should almost be identical. It's everything from 2 on the left out to infinity on the right. Infinities always have parentheses around them, no matter what. The only difference between this illustration and this illustration is on the 2 you have a parenthesis, whereas here you have a square bracket. So in the interval notation, that will also be the only difference. Exclusive inequality versus inclusive inequality. And finally, this one, again, this illustration is almost identical to this illustration, so they should be very similar. Going from left to right, you go from negative infinity up to 2. Infinities always have parentheses around them, no matter what. Notice, these can change around the constants, but around the infinities, you always have parentheses. Here, around the number 2, we have a square bracket that signifies that that 2 is part of our solutions. And so that means that on this interval notation, around the number 2, we should also have a square bracket. For the most part, this is the way we want to write our answers. It's descriptive. It tells us everything the number line tells us, but without having to go through the trouble of drawing and labeling out the number line. Interval notation is generally the way we want to write our solution sets for interval notations. Sorry, for inequalities. We want to use interval notations to write our solution sets for inequalities. Now, aside from interval notation, there's also one other notation which is not used as often, but can still be used to represent these kinds of inequalities. Essentially, we use this as it is while signifying that it is not just a single solution that we're looking for, but an entire set of things that we're looking for. So this is called set builder notation. And I'll go ahead and put this over here. Okay. And here, this relies on the fact that these are already pretty descriptive on their own. We want every number that's greater than 2. Okay, so that is sufficient to give me a solution, isn't it? Well, see, that's the problem. We don't want a solution. It's true. If I said x is greater than 2, I could determine that 5 is a solution to this inequality. But what I want to do is I want to signify the fact that I don't want just a solution. Here, this is representative of all solutions, every number that's greater than 2. So the way we write that is we're going to write it as a set. These curling braces are used around sets, and a set is going to be written using this description. Okay, so how do we write that? Well, what we want is we want solutions. We want x's. Okay, so let's write that. We want x's. Okay, but what x's do we want? Do we just want any x? No. We want x's that match a particular description. Okay, so we're going to put a bar right here. And this bar separates the two parts of our set builder notation. This represents, here's what I want. I want a single number. If you wanted ordered pairs, you could say I want x comma y. Whatever it is you're looking for, whatever your answer is supposed to look like, that goes here. And then after the bar, you want to write a description of what these answers are supposed to be. Oh, I want to find the set of all x's. Oh, which x's? Oh, the ones that are greater than 2. And there we go. This is the set builder notation, and it describes the same thing that this interval notation does. Likewise, here we could say I want the set of all x's. Which x's? Oh, the ones that are less than 2. Note, set builder notation is not different than interval notation. Rather, it is an alternate way of expressing it. It doesn't say anything different, it just shows it in a different way. You might wonder why there's two different notations. Set builder notation is often used when interval notation is difficult or clumsy to write. Some more advanced sets would be difficult to write out in interval notation because of all the conditions that they have. When you have very few conditions, interval notation is often simple because it shows you from left to right, here's exactly what I want. When things become more complicated, set builder notation is often useful because instead of having to figure out how to write or draw or express that, you can simply list the requirements. Here, this would be x. Incidentally, this bar that separates your object from its description is usually read as such that. So here we want the set of x's such that x is greater than or equal to 2. And again, this is usually read as such that. And finally, this last one, x such that, I want the set of x's such that x is less than or equal to 2. And set builder notation is another way of writing out the results that come about from a linear inequality in one variable. So from these illustrations, it becomes apparent that inequalities are different than equations. They express something different. If I said x equals to 2, there is exactly one number that makes that true, the number 2. All right, x is the number 2, and that's it. It's the only number it can be. With an inequality, you have an entire collection of numbers, an entire part of your number line which represents your solutions. So the interpretation of an inequality is different from that of an equation. It means something different. It says something different. Fortunately for us, the way we solve inequalities is going to be very similar to the way we solve equations. In fact, they're so similar that there's only one real difference. You'll recall the addition and subtraction properties of equality. The addition and subtraction properties of equality state that if you start with two things that are equal, say A is equal to B, then you can add the same thing to both sides and both sides will still be equal. Well, the same thing is true for the inequalities. Just like you have an addition and subtraction properties for an equation, you also have the exact same addition and subtraction properties for inequalities, which state that if A is greater than B, then you can go ahead and add something to one side, and as long as you add the exact same thing to the other side, the inequality is preserved. It's still greater on this side than it is on this side. Or, if you want to go ahead and subtract from both sides, that will still preserve your inequality. So you can add or subtract on both sides and your inequality is maintained. And it doesn't matter what you add or subtract as long as you do it the same way on both sides. Subtraction or addition both work the same way. And it'll work for this kind of inequality, or it'll work for, we can reverse the direction. If instead of A is greater than B, we can say A is less than B. I can add or subtract on both sides and still maintain the equality. So if A is less than B, then A plus C is also less than B plus C. And if A minus C would also, and if A is less than B, then A minus C is also less than B minus C. So it doesn't matter if you add or subtract, your inequality is still maintained. And that happens whether your inequality starts off as a greater than or a less than, or if it's a inclusive inequality, it maintains that as well. So if I start off with A is greater than or equal to B, and then I add something on both sides, well then it'll still be greater than or equal to. And the same thing will happen if I subtract something on both sides. And if I have the other inclusive inequality, if I have A is less than or equal to B, well then if I add the same thing on both sides, then this A plus C is less than or equal to this B plus C. And if I subtract the same thing on both sides, this A minus C is less than or equal to this B minus C. Like that. This may seem like a lot, but you don't really have to memorize 12 different things. Essentially, you just have to remember if you have an inequality, you can add or subtract on both sides, and the inequality doesn't change. Whatever it started as, it stays that way. Now, multiplication and division principles of inequalities are almost the same for equations. For equations and inequalities, the addition-subtraction properties are identical, but the multiplication and division properties are slightly different. Here, it starts off looking very much the same. If we have A is greater than B, okay, then if you multiply on both sides by the same thing, your inequality is maintained. And if you divide on both sides by the same thing, your inequality is maintained. Now here's what the difference is. In this case, up here, you could use any number you wanted. There was no restriction. As long as you added the same thing on both sides, it was fine. And there was no other qualifications there. However, here, what we have to say is this is only true if C is positive. If C is positive. It can't be 0 because, well, division by 0 is undefined. But if it's negative, then what that does is it reverses the inequalities. So here, if A is greater than B, then A times C is less than B times C if C is negative. And likewise, A over C is less than B over C if C is negative. And this will be true of all of these other ones. If I start off with greater than, it'll stay greater than as long as I multiply or divide by a positive, but it'll reverse to less than if I multiply or divide by a negative. Likewise, if I start with less than, it'll stay less than if I keep C as positive. However, if I start off with a less than inequality like this, and I multiply on both sides by a negative number, then this less than becomes greater than. It reverses the inequality. And that would also be true of the inclusive inequalities. Here I wrote it just for the exclusive inequalities, but this will also be true for the inclusive inequalities. This may seem like a lot to remember, but you can boil it down to just a simple statement. If you have an inequality, adding or subtracting will not change your inequalities. Multiplying or dividing by a positive will not change your inequalities, but multiplying or dividing by a negative reverses the inequalities. Right? So, two statements. The first one, addition and subtraction properties. As long as you add or subtract the same number on both sides of these inequalities, the inequality will not change. That's it. That's the entire property. For multiplication and division properties, if you multiply or divide on both sides of an inequality by a positive number, nothing changes. If you multiply on both sides by a negative number, the inequality reverses. Whatever it started at, it's going to flip over. Whatever it started as, it's going to flip over like that. Why should that be? Well, just think about a number line. In fact, I happen to have a nice number line right here, yeah? Or at least a ruler. If you have a number line, remember, greater numbers are to the right and lesser numbers are to the left, right? Lesser versus greater. Okay, so let's say I were to add, let's say I have this number compared to that number, right? And 4 is less than 9. Well, let's say I add 1 to both of those numbers. Well, now 5 is less than 10. Yeah, that's still true. Let's say I went ahead and subtracted 1 from each of those numbers. Okay, so now 3 is less than 8. But yeah, that's still true. The stuff that's on the left is still on the left, and the stuff that's on the right is still on the right. So adding or subtracting doesn't change anything. It doesn't matter what I add or subtract. I can even add 0 if I wanted. If I start off with 4 is less than 9, and then I add 0 to both, well, I'm still left with 4 is less than 9. Nothing changed. So adding or subtracting does not change my inequalities no matter what I do. What about multiplying and dividing? Okay, well, let's see. Let's say I have 1 is greater than 2. Oh, sorry, I said that backwards. 1 is less than 2. 1 is less than 2. Okay, let's say I multiply both of those numbers by the number 2. Okay, so now 1 becomes the number 2 and 2 becomes the number 4. Okay, but still the one on the left is on the left and the one on the right is on the right. All right, 1 is less than 2. Okay, 2 is less than 4. They got further apart from each other, but still the one on the left stayed on the left. The one on the right stayed on the right. And if I divide, well, the same thing will happen. Let's say I have 3 is less than 6. Let's say I cut both of those in half. Half of 3 is 1.5, and half of 6 is 3. But still, the one that was on the left stayed on the left. The one that was on the right stayed on the right. So multiplying or dividing by a positive, everything stays the same. But think about what happens when I multiply or divide by a negative. Let's say I have 1 is less than 2. All right, well, what happens if I multiply by a negative number? Well, 1 becomes negative 1, and 2 becomes negative 2. Well, yeah, but if I'm on that side of the number line, look what happens. It flips around. So now negative 1 is over here, and negative 2 is over here. All right, if this is 0, 1. Now, if this is 0 right here, and that's 1 and that's 2, if I take 1 and multiply it by a negative, I get negative 1. If I take 2 and multiply it by a negative 1, I get negative 2. Oh, notice those just switched over each other. The one that was on the left and the one that was on the right. Hey, look, the one that's on the right is now further left. Because whenever you multiply or divide by a negative, you switch to the opposite side of your number line. What that means is whatever number line you had from before, it's now being reflected. It's now being flipped. So this flips over and it's now backwards. Oh, but if everything's backwards, that means your inequalities are reversed. Whatever was on the left before is now on the right. Whatever was on the right is now on the left. And so everything is now backwards. So let's see how to use this to solve inequalities. And when we solve our inequalities, we're going to go ahead and write our answers either in set builder notation or in interval notation. Okay? All right. So let's just start with a nice example. And in fact, let's do an example of an inequality alongside an example of an equation just to compare and see how they really are very similar. So I'm going to go ahead and solve. 2x minus 15 is equal to 31. And I'm also going to do 2x minus 15 is greater than 31. This is an inequality. This is what I'm working on. This is what this section is about. But I'm going to solve an equation at the same time just to compare what the two look like. Think about an equation. What would be the first thing you do here? You would add 15. You would add 15 to get rid of this minus 15 because you're trying to get the x by itself. Well, yeah, but with an equation, whatever you do on one side, you're going to do on the other side. So let me add 15 over here as well. So that's going to give me a 2x. That's gone. And now 15 plus 31 is 46. Now, to get that x by itself, I want to get rid of that 2. Okay, so I can divide by 2 on both sides. 2 divides 2 to give me 1. That's the number 1 times x, which is just x. 46 divided by 2 is 23. And that's my solution. I have x is equal to 23. Now, compare that to this inequality. Yeah, an inequality means something very different from an equation. The interpretation is different, but the way we solve is going to be very, very similar. We still want to figure out what x is, which means we still want to isolate. So we want to get rid of this 15. But the only way to get rid of this minus 15 is to add 15 right there. We see, however, in our addition property that that's fine. I can add whatever I want to either side as long as I do the same thing to the other side. And when I add, the inequality doesn't change. Okay, so that's fine. I can add 15 to both sides of this inequality. 15 minus 15 goes away. And I'm left with 2x is greater than 46. Different symbol, different meaning. It looks very similar otherwise. I want to isolate my x, which means I want to divide by the number 2. Okay, 2 divides by 2 gives me the number 1. That's 1x. That's what I was after. On this side, 46 divided by 2 is 23. This is not an equal sign. It's a greater than symbol. So there's our result. Notice that in spite of the fact that these inequalities mean something very different than these equations, they have a very similar procedure to solve. Here, there is one number, and only one number that works as a solution, the number 23. Here, we can have any number as a solution as long as it's greater than 23. We could use 24, 25, 29, 150, 9 million. Any of those are fine. These have very different answers and a very different interpretation, but the procedure is almost exactly the same. Finally, we want to go ahead and write this one in interval notation. Here, with a solution, just a single point, you just write down that number. But here, we're going to go ahead and write this as a interval. Usually this part just happens in your head. You visualize this, but since you can't see inside my head, I'm going to have to draw it out. You imagine a number line, minus infinity to infinity. All right, so what I want is starting from the number 23. Okay, so here's 23. I want everything greater than 23. Okay, well, greater is to the right. Oh, but I don't want to include 23. This is exclusive. Okay, so I'll use a round parenthesis. So all of this part usually happens in your head. If you want to draw it, that's acceptable. That's fine. You can draw it whatever you need to. But what you really want to answer is this result in interval notation. I want everything starting from 23 on the left out to infinity on the right. We have a round parenthesis around 23 because that's an exclusive inequality. And around infinities, you always have parentheses no matter what. And there we go. There's our solution. Different interpretation, different looking answer, but the procedure is very much the same. So if ever you get stuck with solving an inequality, ask yourself, okay, forget about an inequality. What if this was an equation? What would I do then? Whatever you would do for an equation, that's probably the right thing to do for an inequality also. Let's take a look at another example. Let's go ahead and solve the inequality. Let's do 5 minus 3x is less than or equal to 17. All right, so here we go. Same thing, we want to isolate our variable x. We want that x by itself. So let's get rid of this 5. Notice, since that's a positive 5, I need to subtract it. 5 minus 5 gives me 0, which is what I want. I want 0. I want that to go away. And that'll leave me minus 3x. Now remember, adding or subtracting doesn't change your inequality. So here, less than equals to will remain as less than or equal to. And 17 minus 5 is 12. Now I want to get rid of that negative 3 so that I can get that x by itself. So what I want to do now is I want to divide both sides by a negative 3. That way, negative 3 divided by negative 3 is the number 1. That's what I want. I want 1x. But notice, I've divided by a negative. And from our properties that we see here, if you either multiply or divide by any negative number, your inequality will reverse. So if it started as greater than, it'll become less than. Or if it started less than, it'll become greater than. So here, this is less than or equal to. Okay, so it'll switch to be greater than or equal to. It doesn't affect the equal part, only the directional inequality. And then 12 divided by negative 3 is negative 4. And so now we can write out our answer. Again, visualize this as a number line. If you draw it, that's fine. And if you just do it in your head, that's fine too. After a while, once you've drawn it enough times, you'll just start to visualize that. But until such time that that becomes comfortable, drawing it is a perfectly good way to do it. So here from negative infinity to infinity, here's my negative 4. And I want everything that's greater than negative 4. Okay, greater is to the right. Well, greater than or equal to. Okay, so I want to include the negative 4 also. So I do that with a square bracket. Okay, so my interval notation is everything starting from negative 4 on the left to infinity on the right. We have a square bracket around the negative 4 because this is an inclusive inequality. And around infinities, we always use a parenthesis no matter what. There we go. This is our solution in interval notation for this inequality. All right, so go ahead and give this a try. Based off of these two examples here, go ahead and solve. We'll do 7 minus 5x is greater than 42. Go ahead and solve and write the result in interval notation. Pause the video and go ahead and go through that, and once you have a result, go ahead and unpause and we'll go through it together. Alright, so we're going to solve this inequality. We want to get that x by itself, so let's begin by subtracting 7 from both sides. That way 7 minus 7 will give me 0. That goes away, and I'm simply left with a minus 5x is greater than 42 minus 7 is 35. Notice my inequality hasn't changed directions because I can add or subtract whatever I want, and that doesn't affect anything. Next, let me go ahead and divide both sides by a negative 5. That way, negative 5 divided by negative 5 is positive 1, which is what I want. I want 1x by itself. But now, since I've divided or multiplied by a negative, you can add or subtract whatever you want. But if you multiply or divide by a negative, now your inequality reverses. So that's now less than. 35 divided by negative 5 is negative 7. And there you go. There's our result. Now we're going to write this in interval notation, visualizing your number line from negative infinity to infinity. Here's our negative 7. Okay. We want x is less than negative 7. Okay, so less than is to the left, going this way. We don't want to include negative 7. That's not inclusive. An exclusive inequality will use parentheses. All right, so now in interval notation, from left to right, we're going to go from negative infinity up to negative 7. Negative 7 has parentheses around it because this is an exclusive inequality, and you always put a parenthesis around infinity no matter what. And that is our result. Now, as with equations, sometimes your inequalities will start off just a little bit more complicated than we would like. So we may need to simplify our inequalities before we start to solve. So let's consider the following example. Same kind of problem we're going to solve. And we want to write our answer in interval notation. But now our problem is going to look just slightly more complicated at the beginning. We're going to say 2 minus 3 times 4x minus 5. You can tell I work very hard to come up with examples, right? 2, 3, 4, 5. Is going to be greater than or equal to, let's say, 6x minus 3 times 4x plus 1. Okay? So now we're going to solve our inequality. But before we do, we need to simplify things. Notice we simplify things completely independent of the fact that this is an inequality. When you simplify an equation or an inequality, you simply look at the expression on one side and you simplify. You distribute and combine any like terms that you can. Separately, looking at the other side, not as an equation, not as an inequality, but as just an expression, we distribute and then we combine like terms. Once things have been simplified, then we can worry about solving. So right now, this is not an equation and it's not an inequality. It's only a single expression, 2 minus 3 times 4x minus 5. So to simplify this, we're going to start by distributing. I'm going to go ahead and take my negative 3 and I'm going to distribute throughout this expression. Remember, multiplication comes before any addition or subtraction, so distributing goes first. This will give us 2 minus 3 times 4x, that's minus 12x. And minus 3 times minus 5, negative times a negative is a positive 15. And notice now these two numbers can be added together. They're just regular real numbers. 15 and 2 make 17. So this gives us minus 12x plus 17. Now on the other side of my inequality, I have to do the same thing. I'm going to start by distributing. This negative 3 will distribute here and here. And this will give us 6x minus 12x minus 3. Negative 3 times 4x is negative 12x. Negative 3 times 1 is negative 3. And now these can be combined. They're like terms. 6x minus 12x, that's a negative 6x minus 3. Here, we haven't changed either side. We've rewritten it, we've simplified it, but nothing's changed. So here, this inequality has no reason to reverse. Things reverse when we multiply on both sides by a negative number or divide both sides by a negative number. Now you might say, well, wait a minute, I thought that's what we did. That's a negative 3, and you multiplied. Why didn't that change your inequality? It's because that negative 3 was already there. Remember, the properties of inequality state that if you start with an inequality and then you introduce something new, that reverses your inequality. All right? If we start with an inequality and then we multiply or divide by a negative. Notice, these weren't there to begin with. We introduced them later. That's what causes the inequality to reverse. But right here, we didn't introduce anything. That negative was already there. It was already part of the problem. So, by distributing it, we're not introducing anything new. We're just rewriting what was already there. And so that will not change your inequalities. Okay. Next, what we want to do is we want to isolate our variable. Well, you notice the variable exists in more than one place, so let's get rid of it from one place. Here, let me go ahead and add 6x to both sides, because I really don't want to have multiple instances of my variable. I just want all my variables all together. So here, I'm going to pick on the smaller of the two numbers. I'm going to add 6x. That way, plus 6x and minus 6x give me 0. Okay? I'll pick on the number with the smaller absolute value. Over here, if I take negative 12x and I add 6x, I get a negative 6x. So negative 6x plus 17 is greater or equal to negative 3. This is starting to look a lot more like the previous example that we had. Let's go ahead and continue. We're starting to see our results show up here. We're trying to get that x by itself, which means we now need to get rid of this 17, which we can do by subtracting 17 on both sides. So 17 minus 17, that's 0, that goes away. And that gives us just minus 6x right here is greater or equal to minus 20. And finally, to simplify and isolate our x, we want to go ahead and divide both sides by negative 6. That way, negative 6 divided by negative 6 is positive 1. Okay, so that's 1x. Now notice, we introduced division by negative 6. That wasn't there before. There was no division by negative 6 above. So we introduced that number. Okay, so now we introduced multiplication or division by a negative. That's what reverses the inequality. If there's already a multiplication or division already in there, that doesn't do anything. It's when we introduce it. That's what causes your inequality to change. A negative divided by a negative is a positive. 20 divided by 6, well, that doesn't divide evenly, so let me just reduce it. 20 and 6, I can divide the top by 2. That'll give me a 10. I can divide the bottom by 2. That'll give me 3. And there we go. So this isolates our variable. We get x is less than or equal to 10 over 3. Notice a negative over negative gave us a positive here, so it's just positive 10 over 3. And so now we're going to write this in interval notation. Visualizing our number line from minus infinity to infinity, what we want is, starting from 10/3, we want everything that's less than or equal. Okay, well, less than means to the left, and then equal, we use a square bracket for that. So now from this illustration, we can write out our interval notation. This is negative infinity up to 10/3. We have a square bracket on the right around the 10/3, but on the left around the infinity, we always have parentheses around infinities. So that is our solution written in interval notation. Note that the simplification looks identical to what you would do to simplify an equation. It's once you have it simplified, that's when things can start to change a little. All right, so go ahead and give this a try. You're going to go ahead and take the following inequality and go ahead and solve and write in interval notation. Let's try 6 minus, let's say 6 minus 2 times 3x plus 1 is greater than or equal to, let's try 4x plus 2 times 2x minus 8. All right, go ahead and pause the video and give this a try. Once you have a solution written in interval notation, go ahead and unpause the video and we'll go through and confirm the result together. All right, so let's give this a try. We're going to begin by simplifying. Here, let me distribute. And so I have 6 minus 2 times 3x will give me 6x. And minus 2 times 1 will give me minus 2. Remember, the negative is part of the number, so when you distribute, that negative 2 gets distributed to both of these numbers here. Okay? And then I can combine like terms. I have a 6 and a minus 2, so that's minus 6x plus 4. On this side, I can distribute this 2 there and there, and that'll give me 4x plus another 4x minus 16. I can combine these two numbers. That's 4x plus another 4x will give me 8x minus 16. And now we have each side as simple as we can make it. Well, now what we want to do is we want to simplify by getting rid of one of these. It doesn't actually matter which one we get rid of. But personally, I like to keep all my variables on this side. That's just the way we usually write our inequalities or our equations. So here I'll proceed to get rid of this one here. I'm going to subtract 8x from both sides. And that makes this go away. All right, so 8x minus 8x is gone. Leaves me just my minus 16. Now all I've done is I've added or subtracted. And in this case, I've subtracted from both sides. So the inequality doesn't reverse. Okay? That's gone, leaving me just minus 16. Combining these will give me minus 14x plus 4. And now this looks a lot like our first set of examples, where all we're trying to do is isolate our x. Let's begin by subtracting 4 from both sides. 4 minus 4 is 0, leaving me minus 14x is greater than or equal to negative 20. And finally, I can divide both sides by negative 14. Note that now we are multiplying or dividing by a negative number, and that's what's going to reverse my inequality. So now here, negative 14x divided by negative 14, that'll give me just 1x, which usually we don't write 1x, we just write x. Our inequality has reversed from greater than equal to less than equal to. And now these, negative divided by a negative is a positive. These don't actually divide, but I can divide the top and bottom by a common factor of 2. So 20 over 14, that'll reduce to 10 over 7. I divide the top and bottom by 2. And there we go. Here I have a result, which I can now write in interval notation. Okay. X is less than or equal to 10 over 7. So wherever 10 over 7 is, I want to go to the left of that. Oh, but I also want to include that number. That's less than or equal. Okay, that means I use a square bracket there. So my interval notation is everything from negative infinity on the left up to 10 over 7 on the right. We have a square bracket around the inclusive inequality. And as always, we have a round parenthesis around the infinity. And this is our result in interval notation. All right, the last thing we want to look at now is, let's talk about compound inequalities. So far, all of our inequalities have involved starting from some number, whether or not that number was included, and then going forever in one direction or the other. A compound inequality is an expression with more than one inequality which will bound on more than one part of the number line. The simplest forms of those types of inequalities, again called compound inequalities, are the kind that look like this. X is in between two numbers. Here this would be read as 1 is less than x is less than 5. Now remember, inequalities are relative. So if we say 1 is less than x, that's the same as saying x is greater than 1. So you can also think of this as saying x is greater than 1 and less than 5. Right? So either of those is fine. This can either be read as 1 is less than x is less than 5. And that's the literal way of reading it. You would just go from left to right. 1 is less than x is less than 5. Or, if you like, you can also read it as x is greater than 1, because after all, if 1 is less than x, then x is greater than 1. If I'm younger than my brother is older than me. Right? Here, x is greater than 1 and less than 5. Okay. We would write this in interval notation very much the same way as we write all of our other inequalities, by visualizing it on the number line or by drawing it on the number line and then using the appropriate boundaries, see either parentheses or brackets. So if you have a number line from minus infinity to infinity, notice there's two numbers of interest on this number line that we want to look at, 1 and 5. Remember, 1 is on the left, 5 is on the right. All right, so now we're saying we want every number that is greater than 1. Okay, so to the right of 1. Oh, but we don't want to go forever. We still want the numbers to be less than 5. Okay, so greater than 1, but still less than 5. Okay, so between 1 and 5. Notice we don't want to include the number 1. That's an exclusive inequality. And likewise, the number 5 is also exclusive. Okay, so the inequality from the inequality 1 is less than x is less than 5 in interval notation would be written as 1 comma 5, 1 on the left, 5 on the right, and parentheses around both. just like that. Note that it's possible to have one of these be inclusive and the other exclusive, or you can have them both inclusive, or you can have them both exclusive. And you would use the appropriate symbol for both. So for example, let's say we had again, this would be read as -1 is less than x is less than 4. Or, if you prefer, you can read this as x is greater than or equal to -2 and less than 4. Both of those are appropriate ways of reading this inequality, compound inequality. And to express this on the number line, you would want, here's your -2 on the left, here's your 4 on the right, and you want everything in between those. Right? You want everything that is greater than -2, but that is still less than +4. Note here, we want to include -2. That's an inclusive inequality. So we use a square bracket. But over here, we want to exclude the number 4. An exclusive inequality. We use a round parenthesis. So to write this in interval notation, we would have -2 up to 4 with a bracket around the -2 and a parenthesis around the +4. Just like that. When we solve a compound inequality, we're going to follow very much the same steps that we do to solve any other kind of inequality. The only difference is now, instead of saying whatever I do to one side, I have to do on the other side, well, now you're going to have 3 parts. Okay, so whatever you do to one part, you got to do the other 2 parts. Instead of saying, okay, I have 2 parts, whatever I do on one side, I do to the other, now it's whatever I do to one side, I do to the others. Multiple. Otherwise, it's exactly the same. So, for example, let's go ahead and solve, and we're going to go ahead and write this in interval notation. -5 is less than 4x minus 9 is less than or equal to 1. Okay, again, we're trying to solve for x. Whether it be an equation or an inequality, x represents our solution or set of solutions. So if we isolate our x, that will tell us what our solution or set of solutions are. All right, so let's do that. Let's go ahead and add 9 to every part of our inequality. To try to isolate this x, let's get rid of that -9. And so, whatever we do to one part, we have to do all parts. Okay, so that goes away. Here I have 9 minus 5, that'll give me just the number 4, is less than 4x is less than or equal to 9 plus 1 makes 10. And so now, to get that x by itself, I would need to divide by 4. 4 divided by 4 is just the number 1. So that's the number 1. Right? 1 over 1. Likewise over here, 4 over 4 is just the number 1 times x. Okay, so 1x. And then over here, less than or equal to 10 over 4. That doesn't divide, but it does reduce. We can write that as 5/2. So on the number line, that's all the numbers. Here's 1. Here's 5/2. Remember 5/2, that's 2.5. And we want all the numbers that are greater than 1, but less than 5/2. Okay, so between 1 and 5/2, like that. We do not want to include the 1. It's exclusive. But we do want to include the 5/2. That's inclusive. It's got an equal sign there. So we're going to use a square bracket for that. And so our result is going to be everything from 1 up to 5/2. We do not include the 1, but the 5/2 is included as part of our solution. So we write that in interval notation like that. All right. For our last problem here, go ahead and give this a try. You're going to go ahead and solve. And as always, we're going to write in interval notation. All right. Let's have you try 6 is less than or equal to 5 minus 2x is less than 17. Okay, go ahead and give that a try. Go ahead and write out your solution in interval notation once you're done. Pause the video, and once you're done, go ahead and unpause and we'll go through it together. All right, so we're trying to isolate our x. So let's start by getting rid of that 5. If I subtract 5 here, 5 minus 5 is 0, that goes away. But whatever I do on one side, I have to do on all sides. All right, so that's now the number 1. Less than or equal to negative 2x is less than 12. 17 minus 5 will give me 12. Now, I want that x by itself, which means I now need to divide by negative 2 right here. And whatever I do on one part, I have to do on all parts. But remember, when we divide by a negative, we're going to reverse these inequalities. The fact that we now have a compound inequality doesn't change that. Multiplying or dividing by a negative reverses our inequalities. So here that's going to be negative 1/2. And that's going to be, instead of less than, that's greater than or equal to. That's an x. And here, instead of being less than, that's greater than negative 6. Okay, now think about what that says. This says, here's my number line. I have 2 numbers on here. Now be careful with the order. Even though in this sentence you have your negative 1/2 on the left side and the negative 6 on the right side, that's not how they appear on a number line. All right, negative 6 is less than negative 1/2. Negative 1/2 is really close to 0, right? Just a little bit to the left of 0. Negative 6 is really far to the left. Again, think about a number line. If you have 0, that would be 1, 2, 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, all the way out here. Okay, so now I want all the numbers. Let me just read this one at a time. I want x to be greater than negative 6. Okay, so from here to the right. Greater than is to the right. But over here, I want negative 1/2 to be greater than x. Now remember, inequalities are relative. If I say negative 1/2 is greater than x, the same as saying x is less than negative 1/2. Okay, so I want less than negative 1/2. I want to the left. So here, this is a little misleading. Reading your inequalities, make sure the arrows are in the right direction for what you're trying to say. Here, this is saying I want everything that's greater than negative 6, this way, and less than negative 1/2, this way. So all the stuff between here and here. So just be mindful, this is not necessarily going to be reflected here. The number line has a certain order regardless of what this says. So now we can go ahead and write out our results. Notice right here, this is inclusive, so we want a bracket there, square. Here we have an exclusive inequality, so we want exclusive, we want a parenthesis here. And so our result is everything from negative 6 on the left to negative 1/2 on the right, parentheses around the negative 6, and brackets around the negative 1/2. And that is the result of our compound inequality written in interval notation. All right, so that is it for our problems for this video. If anybody has any questions, comments, problems, please make a note of those and reach out. And I hope everyone has a nice day.